and I'll tell you a bit today about what Flux is and what it can do. So what is Flux at the highest level? Flux is a resource manager like Slurm, LSF, or PBSPro. It usually runs across an entire HPC cluster and controls access to the cluster's resources. For instance, say you want to run a physics simulation on 10 nodes of a cluster, you would ask Flux to give you 10 nodes for a certain amount of time, maybe 5 hours or so, just as an example. Flux will make you wait while your job goes through the scheduler, which might take anywhere from seconds to days, depending on cluster usage and your priority as a user. And then you would be granted 10 nodes of the cluster until you voluntarily yield up the allocation or the time limit expires. While you have those 10 nodes, you could ask Flux to schedule and launch applications on them, whether the applications happen to be Python scripts that run for a quarter of a second, or a gigantic C++ executable that uses MPI. Sorry, I'm having some trouble here. There we go. So in addition to running as a cluster-level resource manager, Flux can also operate as a single-user scheduler and execution system, and can bootstrap itself inside of other resource managers' allocations. So you can, for instance, get a resource allocation from Slurm, and then launch Flux within that Slurm allocation. You launch Flux like you would any MPI job. And from then on, you communicate only with Flux and forget that Slurm exists at all until Slurm tears your allocation down. So there's a few reasons to do this. The first and most importantly, because you like the features that Flux provides. And secondarily, because you need to deal with a number of different resource managers, and you want to use Flux as a kind of portability layer. For instance, if you were developing a workflow tool that needed to support PBSPro, Slurm, and LSF, you could write the logic for handling each of those different resource managers, or you could just launch Flux and forget about all the complexities and idiosyncrasies of the other resource managers. However, you would still need enough resource manager-specific logic to be able to launch Flux within those different allocations. So due to its ability to run within the other resource managers, Flux is not needed to wait for HPC centers to convert their clusters wholesale to Flux in order to get real usage. Flux currently has, and has had for years, users at many DOE facilities, including Livermore, where it's developed, Lawrence Berkeley, and Oak Ridge. And due to the promising results that Flux has enabled, Flux won an R&D 100 award in 2021. So Flux is beginning to get some experience as an official cluster-level resource manager, though. As of the past year or so, Flux has started to be deployed on some smaller Livermore clusters. The list of clusters currently running Flux includes Tioga, Hetchy, Corona, Fluke, Elmer Fudd, and just this week, RZ Vernal and Tenaya. For the most part, these are smaller, but Tioga, Vernal, and Tenaya all place in the top 200 on the top 500 list. So when I say they're small, they're still pretty powerful. And pictured here is Corona. Most importantly, however, Flux is planned to be the system resource manager on LCAP, which is Livermore's next huge supercomputer, and which is being delivered to Livermore from now until the end of the year. I happened to see, actually, some of the first infrastructure racks being installed just a few days ago. Flux more or less has to be the system resource manager on LCAP, but I'll go more into that later. And the three early access machines, the three machines I mentioned that are on the top 200 list, Tioga, Tenaya, and RZ Vernal, are actually early access machines for LCAP, which is why part of the reason they run Flux. Livermore is also converting existing Slurm clusters to Flux, but due to user inertia, it's coming along pretty slowly. Users don't like change, and the switch to Flux would cause a lot of intense frustration as users have to convert their scripts to a new resource manager. So are there any questions on this? This is like the very basics of what Flux is and what it does. Are there any questions so far? Cool. Okay. Just wanted to check to make sure that the basics are settled. So probably the most important question is, why did Livermore choose to develop another resource manager when there are already several out there with proven track records? There are a couple of reasons. So the people originally behind Flux, of which I'm not one, I'm not originally behind Flux, noted significant trends towards complex workflows, extreme resource heterogeneity, and converged computing, which are rendering traditional resource managers increasingly ineffective. There are 5 principal challenges. 1 second. The first is the co-scheduling challenge, where complex workflows require component coupling and co-scheduling of different types of hardware, such as CPUs and GPUs and other hardware accelerators. The second is the throughput challenge, where uncertainty quantification and other ensemble-based techniques can submit tens of thousands of short-running jobs which overwhelm traditional HPC resource managers. For instance, a year ago, when the Cori supercomputer at Lawrence Berkeley was still active, users were expressly prohibited from launching more than a certain number of srun commands in their allocations because each srun required communication with the central Slurm scheduler. And so a single user launching a lot of sruns on one small portion of the cluster could degrade performance for every other user on the system. Livermore also had, and perhaps still has, a similar limit for the same reason, but I haven't verified it. I know it existed a few years ago, but I haven't checked it. It's still around. You have to launch a lot of sruns to make sure that it still exists. And actually, a matter of fact, I noticed that Jan Jansen mentioned the Lawrence Berkeley srun limit in his talk on PyIron on Monday. So the third reason for the development of Flux is the job communication and coordination challenge. In this case, workflows depend on data transfer between various components within a framework. There may be need for a lot of synchronization, or there may be a number of dependencies between jobs. And a resource manager which can help with communication and is aware of dependencies would be a huge improvement. So the fourth benefit, or the fourth challenge, is the portability challenge. In order to make sure that an application runs across multiple platforms, application developers and engineers need to port an application to a large variety of resource managers. Just at Livermore, we now have 3 resource managers in active use: Flux, Slurm, and IBM LSF, which is used on our CRS systems. Other sites use other resource managers, and then also, in my experience, Slurm at other sites frequently behaves differently from the Slurm I'm used to at Livermore. So sometimes it's not enough to just support Slurm. You have to support different varieties of Slurm. This was true on a workflow system I used to work on. We had like a specific variety called LLNL Slurm that we supported because of the differences between the way that LLNL Slurm behaved. And finally, we're starting to see extreme resource heterogeneity, which stretches or exceeds the resource model capabilities of traditional resource managers. I mentioned that Flux more or less had to be the resource manager on LCAP, and that's due to the unusual design of LCAP. I'll go more into it later, but it was determined that without substantial modifications, other resource managers could not make LCAP fit into their resource models well. So to give a concrete example of a workflow that strained a traditional resource manager, in this case it's IBM LSF on our CRS systems, I want to talk about the multi-scale machine-learned modeling infrastructure called MAMI, that's M-U-M-M-I, which couples a macro-scale model spanning micrometer length and millisecond timescales with a micro-scale model employing high-fidelity molecular dynamics simulations to model RES protein interactions with cell membranes. RES protein mutations are involved in a large number of cancers. The workflow used up to 4,000 nodes of the CRS supercomputer, concurrently utilizing over 16,000 GPUs and 176,000 CPU cores, and running up to 36,000 different tasks with large length and time scales, yet at the same time, molecular level details. So there were 4 coarse-grained simulations, that's 1 per GPU, on each node. Each coarse-grained simulation would be bound to 2 CPU cores that share cache. The corresponding analysis jobs occupy 3 cores for each coarse-grained simulation, totaling to 20 cores. Totaling to 20 cores utilized by the coarse-grained simulations. In order to reduce latency and communication with the GPUs, this 20-core partition is bound exclusively to the cores closest to the PCIe buses. The remaining 24 CPUs per node, are dedicated to CPU-only jobs and are either the macro simulation, a setup job for the coarse-grained simulation, or the workflow manager. With coarse-grained simulation jobs in groups of 4, several thousand jobs run concurrently. Avoiding resource oversubscription or placing too many jobs in the same node requires the ability to co-schedule multiple jobs on the same node based on heterogeneous resource requirements. That's one of the areas where Flux shines, and it was determined that the native resource manager could not meet the demands of the MAMI workflow. In fact, In order for MAMI to start up 36,000 concurrent tasks, the team exploited Flux's ability to hierarchically schedule subinstances of itself and to specify explicit bindings of resources. But I'll go into later in what it means for Flux to be able to hierarchically schedule subinstances of itself later. That is a topic that takes a bit of explanation. The results of this effort resulted in a paper that won SC19 Best Paper and I think a few other awards as well. So more generally, at Livermore, we found that our newer workflows are demanding more portability, more dynamism, and cloud integration. For instance, a 2020 lab survey found that 73% of Livermore workflows were interested in cloud integration. The American Heart Association's MOLS workflow, called AHA MOLS, uses a scalable message broker to couple MPI-based tasks, analysis, and workflow runs anywhere. More and more of our workflows are making use of orchestrated databases and machine learning, which has led to increased demands on the resource manager to schedule lots of different jobs and lots of different sizes of jobs with quick turnaround. So Flux is responding to these demands by offering a suite of features and behavior that will allow it to meet the needs of current and future workflows while still providing the sorts of features and functionality that users of other older resource managers are accustomed to. So a complete sales pitch for a Slurm user would be that Flux is relatively easy for a Slurm user to learn, that it offers sophisticated configurable scheduling abilities and scalable performance, and that Flux behaves consistently across clusters. Behaving consistently across clusters doesn't mean that Flux isn't configurable, but the meaning of resource concepts like core is consistent, which it isn't always in Slurm, and it's a priority for us to not break user scripts when they transition from one Flux cluster to any other. And for those who want to run Flux under another resource manager, it's easy to build with relatively few dependencies. It can be installed with SPAC and Conda. And the Flux team maintains Flux Docker images for testing out single node deployments. These containers are great for development and continuous integration testing. So if you're writing a workflow tool, you can pull our containers and run tests against Flux in your CI. And you don't need any special GitLab runners to do that. Flux also offers interfaces designed with workflow tools in mind, making complicated job manipulations easy. I'd also say that Flux is pretty well documented, but I think that's better left to your judgment. So to start with the basics of using Flux, Flux's command line interface offers most of the same functionality as Slurm. Flux is, after all, developed by many of the principal engineers behind Slurm. The most obvious difference is that most other resource managers have a number of different commands, like salloc, sq, sinfo, and so on. Flux just offers the Flux command with various subcommands, kind of like git checkout, git branch, and so on. So for a lot of simple use cases for submitting jobs, users can pass the same flags and arguments and expect very similar behavior. For instance, to get a 4-node interactive allocation for 90 minutes in a debug queue, instead of salloc -n4-pdebug-t90, it's fluxalloc-n4-qdebug-t90. The only real difference is instead of p, we have a q, and instead of salloc, we have fluxalloc. It's basically the same thing, in other words. And similarly, to launch an MPI application on 2 nodes with 16 ranks and 2 cores per task and 2 GPUs, the flags are basically identical. You can also see in the pictures I have up that a simple batch script for Flux is very similar to one for Slurm. Instead of #s batch, we have #flux, but by and large, the concept's the same. So here's a more complete table, cross-referencing various commands on 4 different resource managers. 2 of them you might not be familiar with are IBM LSF and Moab. If you've used Summit, you've probably used LSF or Lassen at Livermore. So when it comes to fetching job information, there can be some big differences in how users ask for information and in what format it's presented to them. For instance, instead of the saccount command with all its options, Flux offers both the Flux jobs and Flux job info commands. But again, the concepts are similar, and generally it's just a matter of finding the right command or the right flags. So one of the advantages of the Flux command line is that it offers a command called Flux bulk submit, which has an interface like GNU Parallel, or XArgs if you happen to be familiar with those, for submitting jobs in bulk. And unlike the bulk submission tools for other resource managers, the jobs don't need to be uniform. But the main interface advantage that Flux offers is the language bindings. So the primary interface to Slurm, LSF, Cobalt, and most of the other resource managers that I'm familiar with is the command line, which is why I decided to give a quick overview of the Flux command line first. Flux has an equally sophisticated command line interface as any of those resource managers, but it also offers rich Python and C libraries. Through those libraries, users can do everything they can do on the command line and much more, only with finer-grained control and much better performance. Flux also offers some C++, Lua, Go, and Julia, and Rust support as well, but our Python and C libraries are the most heavily used and therefore the most reliable and complete. Getting the other libraries to work might take some work on the user side. For instance, suppose you're the author of a Python workflow tool that needs to launch a huge number of applications and monitor their exit status. That's possible through a command line interface. You could, for instance, use Python's library for launching processes to invoke the command line interface for one of the resource managers, and then monitor the exit status of the process, perhaps reading its standard output and error. I know of a couple workflow tools that do this actually, and I used to work on one of them. And often this approach involves writing to tiny files to indicate that an application is completed, or to check if it failed. The problem with this approach is that it's complicated for one, and it requires a lot of logic on the side of the workflow tool, and also that it's slow. Creating all those processes and sometimes creating all those files takes time, and for a huge number of applications, that amount of time can actually be significant. The alternative that Flux offers is to invoke a function in the Flux Python library to submit a job directly. The function will perform some network I/O to send a job specification to the Flux scheduler, but it will return control relatively quickly, and it will return an object that can be used in combination with other Flux functions to monitor the progress of the job or to fire off callbacks when the job reaches specific states. So it's easy to build efficient and simple frameworks for handling large numbers of Flux jobs in extremely complicated ways. Flux's Python library offers both an event loop-based interface for asynchronous single-threaded programming and an interface based on Python's concurrent.futures library, which is a slightly different model for asynchronous programming. And I won't go into it, but I'll just say that it involves multiple threads in general. With a bit of work, we could also offer support for Python's async and await syntax, and we've nearly gotten there. We just need some user interest to get it completed and supported in our repositories. So furthermore, there are also functions in these libraries for registering and communicating with services. If your workflow tool is split into multiple components, they can use Flux's communication network to communicate with each other using one of the communication patterns that Flux supports, which includes pub/sub, request response, and send receive. There are also functions for getting and adding information to Flux's key value store, and much more. But the main attraction for workflow tools is usually the job manipulation functions. And here on the right, you can see that there are a bunch of, this is some of the many, many functions we offer in the C interface for manipulating jobs and doing other Flux, and interacting with Flux in other ways. So in addition to interface improvements, Flux also handles jobs differently than many other resource managers in a way that we think generally makes things easier for workflows that use Flux. Early on in Flux's development, the principal developers decided that they wanted resource requests to be consistent across clusters. On many other resource managers, when you request a certain resource set, you may be given considerably more resources than you asked for. For instance, if you launched an MPI application with 10 tasks and request 2 cores per task for a total of 20 cores, you may be given 40 cores because that's just how many cores a single node has, and the resource manager just decided to give you a whole node. Or you might be given 80 cores because the resource manager decided to split your job across 2 nodes and give you all the resources on both, and so on. You can extrapolate for 3 nodes and 4 nodes. The resource manager may just give you more and more resources, and many more than you asked for. With Flux, if you ask for, say, 4 tasks and 5 cores per task, your application will have 4 tasks and each task will have its CPU affinity set to 5 distinct cores. It's not a hard bind, though, so if that's not what you want, you can always change the CPU affinity to be all the cores on a node. And besides, Flux also does have a way to request all the resources on a node explicitly. So in addition, all jobs are given exclusive sets of resources by default. If jobs A and B are occupying all the resources on a node, Flux will not attempt to run another job on that node. If you try to launch an application through Flux and there aren't enough resources available, that job will be held in the Flux scheduler until resources free up. Again, though, if there are ways to explicitly request resource oversubscription, if that's what you want. So in combination, these features mean that if you need to execute a workflow which consists of a well-defined set of tasks, perhaps with some simple dependencies, you can throw all your tasks at Flux and expect them to be handled reasonably and efficiently. Flux will handle the scheduling, and a task will be given only the resources you specified, and all the tasks will have exclusive resources. So there are a couple of workflow tools I know of at Livermore and elsewhere that used to implement their own schedulers to work around whatever limitations of whatever resource managers they supported. Sometimes these workflow tools would explicitly specify the placement of jobs within an allocation to ensure that resources weren't oversubscribed. And frequently, they would have limits on the number of jobs they would run concurrently, again, in an effort to maintain exclusive resources. A lot of those workflow tools have been able to replace all that logic with a few calls to submit Flux jobs and be notified when they complete. We've actually made a lot of progress on Livermore workflow tools by doing supporting just exactly that sort of thing of tearing out their internal scheduler logic and replacing it with calls to Flux. So there's another feature of Flux that's worth mentioning, and that's what we call its fully hierarchical design. I've already mentioned that Flux can be run inside the allocations of other resource managers by launching it like an MPI job. But Flux can also run inside of Flux allocations in the same way. You can partition a resource allocation into several distinct allocations like this. Say you have an allocation of 4 nodes, like in the diagram. You could launch Flux again on each node, giving you 4 resource partitions, each with their own schedulers, their own jobs, and so on. If you wanted to take it to the next level, you could create a Flux instance on each core of every node, which is what we have represented here. So there's one Flux instance controlling all 4 nodes, and we create 4, one on each node, and then to go a little bit overboard, we create a Flux instance on each core. I don't really know why you do that, but just for the purpose of the example, you can do that. And so in any case, what you end up with is a tree or hierarchy of Flux instances, hence the name of fully hierarchical. So the drawbacks of creating a hierarchy of Flux instances is that you have to deal with the additional complexity of talking to different schedulers, and you end up with resource fragmentation. You've created a Flux instance on each node. Heaven forbid, you've created a Flux instance on every core. But all of a sudden, a multi-node job shows up, and it may be very inconvenient to run. You'd have to tear down some of the instances to make enough room for that job to go through the top-level scheduler. Whoops. The advantages are that you can specialize each Flux instance with different plugins or scheduler policies, and that you get better performance. So this is the trade-off: is you have more resource fragmentation but better performance. So when throughput is essential and jobs are uniform, a hierarchy of Flux instances can process and scheduler jobs more quickly because each scheduler has fewer resources to consider and generally fewer jobs to consider as well. Flux's performance can scale more or less infinitely this way. The more nodes in your allocation, the wider and/or deeper the hierarchy has to be, but the performance should be the same. And in fact, I have worked on some papers that more or less prove this to be the case. You can just kind of go on expanding the tree and making it deeper and wider and get the same performance. At Livermore, Flux's hierarchical abilities have been used in a number of workflows and workflow tools, including MAMI, aha-mols, and the uncertainty quantification pipeline. Even if you never explicitly create a hierarchy of Flux instances, every user of Flux as a system instance will end up creating a hierarchy implicitly because the Flux alloc and Flux batch commands implicitly create Flux instances. This might sound a little bit bizarre, but I think I can actually explain it. So Slurm has a distinction between jobs and job steps. A job is usually a request for some number of nodes issued from the login node of a cluster with an sbatch or salloc command. Then a job is free to create some number of job steps, usually with srun commands. By contrast, Flux has no concept of job steps. There's only jobs. When a user on a login node issues a Flux batch command, that is a job for the system instance. But the job happens to be a new Flux instance nested within the system instance. So when the user issues Flux run commands inside the job, those are jobs for the nested instance and not for the Flux system instance. That's why within their resource allocations, users can launch as many Flux jobs as they want without impacting or harming other users. A user on node X launching 1 million jobs has no effect on a user on node Y because they're talking to completely different Flux schedulers. And the system instance, which is shared by all users, has no concept of what users are doing with Flux instances further down the hierarchy. That's quite different from Slurm's behavior, where all job step requests, which again are the equivalent of Flux jobs in Flux nested instances, are routed back to the central Slurm scheduler. And if this sounds nightmarishly complicated, it isn't really. It takes a little bit of getting used to, but I wouldn't be surprised if most of our users at Livermore actually don't even know that their batch jobs are really nested Flux instances. Flux also pioneers and uses graph-based scheduling to manage complex combinations of extremely heterogeneous and diverse resources. Traditional resource managers and their models of resources can't cope with extreme heterogeneity because they are designed when systems were node-centric and data structures they use to define the resource types are usually very simplistic. However, Flux, or more specifically the Fluxion scheduler, uses a directed graph of resources which consists of a set of vertices, which are the resources themselves, as in here, and edges, which define relationships between these resources, elevating resource relationships to an equal footing with resources themselves. For instance, a cluster would be a vertex, and a rec would be a vertex, and the rec vertices would have edges to node vertices, the node vertices would have edges to core and GPU vertices, and perhaps also memory vertices if that's necessary for the resource graph. Or even you can make even other sorts of vertices if you want. There's no stopping you. Graphs can also represent network resources just as well as more traditional node, CPU, and GPU resources. Directed graphs can express complex scheduling logic without changing the scheduler code. Different cluster architectures can be represented with a different graph, but the graph search and matching algorithms would be the same. Another advantage of the directed graph approach is that directed graphs facilitate elasticity and resource dynamism through well-defined procedures. Yeah, go for it.
When you say resource dynamism, if let's say I request a job that's 100 nodes, I just want each node to run one calculation, and then when it's done, I want that node to be released because I don't want to start another calculation, and I also don't want to keep paying for that node. Like right now, we have a super hacky stack of scripts that NERSC helped us get set up a couple years ago that allows us to do what they call job repacking, which is basically allow you to release nodes as the individual jobs being run on them as part of your larger job complete. And thus, you go from paying for 100 nodes to then 99.
Yeah.
Is that possible with Flux?
So, well, I guess the immediate answer to your question is not right now. That's something that we're working on. We need it we need it, so we're working on it. But what's to stop you from just submitting 100 jobs instead of one job with 100 nodes?
That would be because on NERSC, the way that jobs age is only 2 jobs age at a time, which means that if I submit 100 one-node jobs, 2 will start, and then the next 2 will start to age. So instead, it is in my interest to submit to play this game where I submit a small number of jobs with many nodes, and then do some hacky BS to basically have each node running an individual calculation.
Okay.
If the time of the calculations I'm running is much less than my wall time, then I'll just keep launching jobs. Like if I'm asking for a 12-hour wall time job, and each of my jobs, like each max calculation is going to take like 30 minutes, just keep submitting. At the end, I'll have 100 calculations that will be incomplete. But fine, I'll have filled that up nice and kind of densely. But if the calculations that I'm running are more going to be on the order of like 6 to 8 hours, then I don't want, if I finish one, I don't want to start another, because most likely it won't complete and I'll just have paid for all this extra time, which hasn't been useful to me. So in that context, you'd rather just release nodes once their subjob finishes.
Got it, yeah.
I guess couldn't you put like the same release script at the end of a Flux job that was running on a node to release the node?
Well, I think the problem is that there would need to be there must be something you do to release nodes, right?
It's somehow there's an S control. It's like it's
some Slurm specific thing.
So you still could do that.
But it's super hacky. I'm listening to this and I'm like, gosh, how nice would it be if I didn't have to have my Slurm script calling another script, which is calling another script, which is calling fireworks, just so that it could correctly release one node at the right point. It's like teaching someone how to do that, and it literally took a nurse expert to put it together. Anyway, we can talk more offline.
Okay.
We're talking about resource dynamism. And that's
yeah, of course. Thanks. The short answer is you can't do that. We don't have an interface for releasing resources from jobs right now, but it is something we're working on. And the Slurm, whatever Slurm does to do it, wouldn't work because we just don't support that at the moment. But yeah, it's something we intend to support.
Must be talking about this.
Yeah.
So there's complex dependencies here, but can we have asynchronous finishing of tasks as well? So if I submit a job and that time for the job is some stochastic process, so I can have a minimization. There's plenty of different jobs you can imagine where the time to completion isn't deterministic.
Right.
And if I still 100 jobs, those 100 jobs maybe with the same input and input data and same task, but the completion time can vary by some amount. It can be quite stochastic.
I see. So what you're thinking is it's like you have a stream of jobs, let's just say one after the other, and you want
I have package jobs I want to run in. Package jobs I want to run in parallel, and I was trying to continually be doing these type of jobs, but the time to complete of each individual job is a random.
Okay. So I'm guessing what you're imagining is that Flux's dependencies would start your jobs after a set time limit or something, or?
Yeah, we would kind of just take the completed jobs and use them as time goes on.
So I guess I'll get to your question in a second, or did you want to?
Similar part, right? So if I need 4 calculations to be finished to start the next job, but I submit 16 and I take the first 4 that I finished. Right? So this kind of I don't know which 4 I take, and I take the first 4 that I finish, and then I can create the next calculation.
I see.
Maybe we can talk offline.
I think the answer is we can't do that, or Flux wouldn't support that with just a simple interface call at the moment. You'd have to have some extra logic for it. If you just want to start a job whenever another one finishes, you can support that by just adding basically a feature of the job saying start it when this other job finishes. But something like start this job when 4 of this set finish, that's not something we support yet. That answers your question? Yeah. Okay, cool. So resource graphs for large clusters can become quite complex. So Flux uses graph filtering and prune searching to manage the graph complexity and optimize our graph search. Filtering reduces graph complexity. Since the graph model needs to support schedulers with different complexities, Flux provides a mechanism by which to filter the graph based on what subsystems to use. So you can see a simplified example at work here, where we remove the network portion of the resource graph to consider only the containment section. And by contrast, pruning does not reduce complexity, but instead increases scalability. A fast red-black tree-based planner is used to implement a pruning filter for each vertex. That filter keeps track of summary information like aggregates about subtree resources. So in order to make use of the flexibility offered by the Flux scheduler, Flux's job specifications, or job specs as we call them, express the resource requirements of jobs in a graph-friendly format for the scheduler. In general, job specs encapsulate all the information about a job, including program attributes such as arguments, environment and variables, runtime, and task layout for the execution service. Submitting a Flux job is really just sending one of these documents to a particular Flux service that receives and processes them. There's only one non-physical resource type in the overall resource section of a job spec, and that is slot, which represents a schedulable place where program processes will be spawned and contained. You can see that the task section of a job spec references the slot and defines what command will be run. So that covers I think what I consider to be all the important and fundamental general information about Flux. And what I have next is digging into some use cases and research. Yeah, go for it.
Yeah, maybe about GPU support. So if I know, how would I allocate the GPUs with my Flux allocation? Or can I? Because you had this nice example where some tasks were using just the GPUs, and the other tasks were using the CPUs.
So those were different jobs. That this wasn't like, I guess. Were you thinking of like an MPI application where some ranks are using GPUs and some ranks are not?
Yes, and if this is connected to the graphs, or?
Okay, so what I was talking about earlier was a case where there were different jobs, and some of the jobs use GPUs, and some of the jobs are just CPUs. If you wanted to have like an MPI, like one MPI application where some of the ranks use GPUs and some of the ranks are just CPUs, I'm sure there's a way to do that. I'm not sure how much Flux would need to be involved. I mean, you could always just allocate GPUs and then just not use them, but that's probably not ideal. I don't know. I guess, does that answer your question, or? Okay. Okay. So at the beginning of my presentation, I mentioned that Flux will be the system-wide resource manager on the Capitan supercomputer, or I call it LCAP for short. There's a reason why Flux was chosen, and it has to do with some of the peculiarities of LCAP. I want to get into them a bit because I think it's a very interesting use case for Flux and for the Fluxion scheduler, and it also happens to be what I work on. So a lot of the architecture details of LCAP are still closely protected. It's public that LCAP is going to have a multi-tiered storage system centered around nodes called rabbits. There'll be one rabbit per compute chassis, which contains some small fixed number of compute nodes. I believe that on our early access machines, the number is 16 or 18 compute nodes per chassis. Each rabbit node will have an AMD EPIC processor and a collection of 18 SSDs with direct PCIe connections to the compute nodes on the chassis. HPE software will be running on the rabbit node and will allow the SSDs to be dynamically configured to offer either node local storage or storage common to all compute nodes in a job. Node local storage is connected by PCIe. Global storage is connected over the network. Global storage has to be over the network because you might have a rabbit on chassis A supplying storage to compute nodes on chassis X and Y all the way over on the other side of the machine. To which the SSDs on rabbit A has no PCIe connection. But given the network proximity and the fact that our backing file system at Livermore uses hard disks and not SSDs, we expect considerably better performance from the rabbit global file systems than the backing file system. So the fact that rabbits can be dynamically configured to be different kinds of storage makes them difficult to schedule. If a job asks for a global file system, the scheduler needs to be aware that it can pick any rabbit. If a job asks for node local storage, the scheduler needs to be aware that when it picks compute nodes for the job, it must pick compute nodes whose associated rabbit has enough storage available. If a job asks for both global storage and node local storage, well, you get the picture. And in fact, it actually gets worse because there are multiple varieties of node local storage, and a single job can ask for all the varieties of node local storage, and it can even ask for multiple varieties of multiple instances of each kind of storage. Yeah, go ahead.
Sorry, I might miss it, but what is the rabbit? What's the purpose of this? Is this a storage node or what?
So it's a dynamic, I think that the technical name for it is like a dynamic multi-tiered storage solution for increasing storage performance in LCAP, basically.
It's a separate node that does only storage, right?
Basically, yeah.
Manage this storage. Right?
It's going to be, so one Rabbit node per compute chassis or rack, I think more or less synonymous. Yeah, and so it's going to be, it is a node, like it does have a CPU, but the main interest is that it has a ton of SSDs, which can be configured to provide storage to jobs. Does that answer your question? Okay, cool. So there's also the additional scheduling complications that users can allocate rabbits independently of jobs. That's useful for when users want to keep a file system around for multiple jobs to use at different times. But it also means that the scheduler will need to be aware of resource allocations which have no compute nodes associated with them. So that's not the end of it, actually. There are further constraints about the number and types of storage that can be combined in a single rabbit. For instance, there's a limit on the number of SSDs, or sorry, the number of NVMe namespaces supported by each SSD. So trying to create too many different file systems on a single rabbit will fail. The scheduler needs to be aware of that to make sure it avoids that constraint. Also, the Lustre file system is what underlies the global rabbit storage, and one of the Lustre servers that runs on a rabbit requires a unique IP. That means that there can only be one server per rabbit, so the total number of Lustre file systems that can be active on a cluster at any given time is equal to the number of rabbits. So in short, rabbits are kind of a scheduling nightmare. The cute rabbit picture I have up there belies that fact. I think it really should look more like this. But anyway, scheduling rabbits was deemed too difficult for traditional resource managers, and hence the decision to make Flux the resource manager for LCAP.
Yeah.
Yeah.
Are you familiar with the burst buffer product?
Yes.
Cray.
Oh wait, of Cray. Sorry.
The burst buffer product. I'm at NERSC and we had a burst buffer on Cori, and it sounds very similar to the Rabbit infrastructure. I wonder if you can talk about how it's what's different about that, because we use Slurm to schedule the burst buffer, and it worked, but it wasn't amazing. And so I'm kind of curious about what's the add-on, like what's additional with the Rabbit that requires Flux to produce something tailor-made for it.
So I don't know exactly what the burst buffers at NERSC are like. I know that on the CRS systems at Livermore, we have burst buffers, and they only offer node local storage.
Yeah, this is the data warp product from Cray.
Right. So the rabbits will use data warp, but it is, they're developing something new. I mean, users would know that they're using data warp. It's transparent to them, but it is different. But since I'm not familiar with what things are like, you said on Cori, right? I don't want to say too much about it, but I think I'm guessing the difference is the fact that the rabbits can be configured to be different types of storage dynamically, whereas I'm guessing that at NERSC they're fixed to be node local storage, or no?
No, there are different types of storage that you can get from the data warp. Maybe I'll talk to you about this.
Yeah, okay, because I'm quite certain that there is a difference, because it's not just, but I don't know what it is. Yeah. So Fluxions graph approach can, in theory, handle all of the Rabbit scheduling complexity with no code change. The Rabbit nodes are represented as a vertex in the resource graph with edges from both rack or chassis and cluster, representing the fact that Rabbits can be either a cluster level or a rack level resource. SSD namespaces are vertices associated with each Rabbit, and each Rabbit has a single IP vertex to ensure that two Lustre file systems are not scheduled on the same Rabbit. But in the interest of full disclosure, Fluxion is wasteful when it needs to schedule the same resource type multiple times. So due to some of the optimizations that Fluxion uses when exploring the resource graph that I talked about earlier, that filtering and pruning, Fluxion doesn't make the most efficient choices when it needs to pick the same resource type multiple times. This inefficiency affects all jobs. Whoops, I'm sorry, I didn't realize this thing came up. I'll get rid of it. How long has it been there?
2 minutes.
Okay. I don't know if I can get rid of it. I can't.
Move your mouse. I think it should have 2 displays.
I don't know, it's not showing up. Okay. So our current deployments, the user rabbits, make use of some workarounds to get efficient resource choices, but the workarounds will not scale to machines the size of LCAP. However, the fundamental inefficiency is planned to be fixed before LCAP is ready. And we do, in fact, actually have actual Flux and Rabbit deployments at Livermore on the LCAP early access machines. We have 8 rabbits total, spread across Tioga, RZ Vernal, Tenaya, and Hetchy. That's our head system administrator on the left, Pi Watson, and our chief technology, that's Pi, and our chief technology officer, Bronis Dusipinski, on the right, putting the very first Livermore rabbit into a cluster called Hetchy. And one of the reasons I'm certain that the rabbits are not like the burst buffers at NERSC was because Bronis said so. So with our 8 rabbits, we can consistently create both node local and global storage and move data to and from the rabbits. There are still some kinks to work out, especially in our error handling. Not all the kinks are in Flux code. Some is in the HPE code that Flux communicates with to provision the rabbits. But in any case, some hurdles remain. And no users have been able to touch the rabbits yet. They're currently limited to system administrators and developers like myself. But that will change in the coming weeks. So I was going to talk a little bit about another area of development. It's research intensive. It relates to adding a Flux plugin to Kubernetes to change to replace the default Kubernetes scheduler with the Flux scheduler. But it's not my area of expertise, and I'm running low on time, so I think I'm just going to skip through it. But the basic idea is that by replacing the default Kubernetes scheduler with Flux, they managed to get some pretty impressive results. They have gotten workflows to run 3 times faster than the default Kubernetes scheduler with lower variability and deterministic placement. It's not actually, they found it wasn't possible to achieve the same placement with the Kubernetes scheduler, even when specifying affinity or anti-affinity constraints. They also got the MPI operator. They increased the scaling of the MPI operator to scale to thousands of ranks. I think previously it had scaled around to 80. So they got 2 orders of magnitude better scaling than before on Kubernetes. That's about all I'll say about the Fluence plugin for Kubernetes. And we're coming to the end. So that's the high-level overview of the Flux framework. You can find some more information. We're an open source project in active development. The source code is available on GitHub, and the documentation is available on Read the Docs. If you look at our GitHub, you'll see it's composed of multiple repos. Flux core, Flux Sched, which is also known as Fluxion. That's the scheduler portion of Fluxion. The Flux K8s, I think, is now known as Fluence. There are a couple Flux and Kubernetes integrations going around, so we have a lot of name collision. And it's not just the source code, and the documentation is public. All issue tracking is on GitHub. And we regularly have users open issues against our repos or join our Slack channel for more rapid-fire discussions. And these are some of the links to the documentation and repos. The most helpful, actually, may be documentation and guides that weren't written by Flux developers, though, since we Flux developers tend to assume that users know about as much about Flux and resource managers as we do, which generally is not the case, because users don't spend all their time developing a resource manager. So the documentation written by Livermore users and administrators, which is the second and third links under the LLNL.gov, may be more accessible than the Flux documentation. But don't hesitate to tell us if you think our documentation could be improved. That's all I have, yeah.